Hey guys, my name is Jesse. My teammates is Kostov and Divyakna. Today we're going to present this paper from Schindel and other authors called Differential Inductive Logic Programming for Structure Examples. So let's review some of the basics of logic programming. So a term T could be a constant variable or an expression, or you can call it a function that has term 1 to n as the input. An atom is a formula P of T, term 1 to term n. The ground atom has no variables, so that it still can have other terms like constant or functions in this paper, especially. Class is a disjunction of literals, and so here, like generally, a class is just a bunch of atoms connected by logical connectors. But here, let's say the class is just A disjunctive with B disjunctive with other literals. But this paper is sort of transfer it into a definite class where only one of those literals can be positive, so that there will be one positive literals disjunctive with a bunch of negative literals, and then they use the Mobius law to simply pull out the negative negation symbol, and then put the only positive literals on the left on the head, and the others in the body, and that would be the solutions of this paper. And VC is a set of variables in clause C. So, right, it's not changing. Right. Let's say these are the classes here where the logical connectives are the disjunction symbol, and then a definite clause only allows one positive literals, which is here, and that will be put into the head of a definite clause. And then by pulling out simply the negation symbol here, so that we will turn every disjunction symbol into the conjunction symbol. And this is like this. We're good on yes. Okay, so theta stands for the substitution operation. So we're substitute from T term to a variable. And theta applied to the head of rule A is written as A theta. A unifier for a set atom 1 to atom n is just a substitution theta such that A1 theta, I'm not going to read all of this. So an intuition behind this is that so for a formal system, we're only, we're not treating this symbol that has any semantic meanings, so that we have to use this unifier and the substitution to actually bridge the gap between, for example, a constant Alice to the variable, like people variable X. So that this is the intuition behind this. So the ILP problem here is basically formed as a 4-element tuple. Positive examples, negative examples, background knowledge, also called as axioms in some literature, and the language. So we here want to find a set of definite clauses, which is this one, that only such that definite clauses, this set of definite clauses union with the background knowledge can explain everything in the positive examples, but not a single thing in the negative examples. So why did differential inductive logic programming? So it was introduced in the last lecture that the authors, Evan Richard and the other author, find a way to that, if you remember, we had a tree that is from end to end differentiable except for the lowest level where some operations are simply checking the dictionary and replace that. And we found a way to formulate the ILP problem as an optimization problem, so that we can use gradient descent to come up with solutions. And the drawback of the previous differential ILP system is that no function symbols are allowed. If you remember previously, we had a slide that a term can be an F of a bunch of inputs. That's not allowed in the differential ILP paper. And the arity of predicates must be less or equal than 2. The number of atoms must not exceed 2. Every program must be comprised of pairs of rules for each predicate. All of these stuff is to limit the search space so that we can come up with a solution in a reasonable time. And thus, the old differential ILP paper is not unsuitable for complex structure data, such as sequence or trees. We'll see some of the examples in a bit. Unsuitable for complex programs that are comprised of several classes for predicate. So today's paper is differential ILP for structured example. We'll see in a second. So the examples, the first example show us that the input data could be a list. So it could be A, B, C, and it could be D, and B, C, D. And then we can find out, for example, the learned problem could be find out problems that, for example, delete the last element from the list, and then we have a new list. This allow us to do the new kind of problems, sequence or trees, or simply functions of variables here. So the challenges here that this paper addresses is, first of all, we can consider a large number of classes instead of just a limited number of classes in the previous paper. Number of possible ground atoms are infinite because right now we have functions and we allow like more than 2 of the inputs in each function. So there will be infinite numbers of ground atoms. And also we have to keep memory and computation costs manageable. So let's see in this example, let's just check from the positive examples and negative example and see what could be a possible solutions of this. So the background knowledge is just, first of all, we have 2 predicates allowed here. The language and the A is not written out here, but we have Q and P as a predicate. So the background knowledge is Q of B and C, Q of C and B. And then, so the one possible solution is P of X, comma X. So we are learning this from the first 2 of the positive examples where, the X are 2 constants like A and B. The whole purpose of this stuff is to, find some solutions that can explain everything in the positive examples and nothing in the negative examples. So this possible solution explains like the first half of the positive examples. Let's check the negative examples. Predicate P with input A and B is this one does not violate that. So this is a possible example solution. The second one is that we want to find something that explains the second half of the positive examples, right? But the predicate used in the negative examples and the second half of the positive examples are the same. They're also P. So this solution here are basically saying that if X and Y can be used in the Q predicate, then we imply that P can be also used on this set of variables. And that does not violate with the negative example.